If you ever worked in a 3D software, you know that there are three main ways to transform an object: translation, rotation, and scaling. Translating and scaling objects are very easy. To translate, you simply add the offset to the coordinate you want to move in. To scale, you multiply the coordinate you want to scale by the scaling amount. What about rotations? It's definitely not as simple as addition or multiplication. Let's try to find out how rotations work without making any assumptions and without taking any shortcuts. Let's invent rotations. First, we need to think about the properties of rotations and how they differ from other transformations. Rotations are not commutative. Because addition and multiplication are commutative, any translation or scaling you do is also commutative. But if you were to rotate a cube first on the x-axis, then the y-axis, the result is different from if you do first y, then x. Rotations are rigid transformations. They preserve lengths and angles. And if you preserve all lengths and angles, you also preserve all areas and all volumes. And if you extend that reasoning, you will see that it also preserves orientation, in the sense that you can't rotate your left hand to get another copy of your right hand. And that's it. Surprisingly, these two ideas are enough to fully define what a rotation is. Now, all we need to do is to find an operator that transforms a vector while keeping its length and orientation constant. Let's say that we have the unit vector x, and we want to rotate it such that we get the unit vector y. So that's a 90-degree counterclockwise rotation. Let's think about what our rotation operator could look like. We want to define an operation that takes x to y. What can we do to get this kind of relation? There aren't really any elementary operators that take a basis vector to another basis vector. We generally treat them as two completely separated objects. Okay, we're kind of stuck. Maybe let's think of something similar. If I give you the number 3 and ask you to find an operator such that when applied to 3 gives the result 5, what would you do? It's very simple, right? The operator in question is 5 over 3. When you apply 5 over 3 to 3, you get the result 5. 5 over 3 essentially means destroy 3 and put 5 in place of it. What if we apply the same logic to our vectors? We want to create an operator that destroys x and puts y in place of it. We can borrow the division notation from standard algebra and use it for our vectors. Something like y over x. Now, this is not standard notation in any way, but just run along with it. 1 over x is just a concept we invented as an inverse of x. When they are multiplied together, they result in 1. Then y times 1 is just y. This might seem kind of arbitrary, but who's gonna stop us? Math police? We can do whatever we want in the process of invention. By the way, from now on, I will be writing 1 over x as x bar. It's the exact same thing, it's just less cluttered, and it makes the order of operations clearer. Now, there is one difference between 5 over 3 and 1 over x that we definitely can't ignore. We can't assume that x bar y is the same thing as yx bar, like we do with 5 times 1 over 3 and 1 over 3 times 5. We said that rotations are not commutative, so we shouldn't assume the commutativity of any operation. Instead of saying multiply by y, we have to say either multiply by y from the left or multiply by y from the right. However, there is one thing that we can show to be commutative right away. X bar equals x bar x equals 1. This is because just like how x bar is the inverse of x is the inverse of x bar. It is a two-way relation. Either they are both inverses of each other or they are not inverses at all. We can also make the same argument for y and y bar. X and y are simply different labels for our unit vectors. They should both act the same. So a rule we define for x should also hold for y. That means y bar equals y bar y equals 1. We can call this yx bar operator the left rotate counterclockwise 90 degrees operator. We call it a left rotation because it is applied to x from the left. Now, what should happen when this operator, yx bar, is applied to y? Rotating y 90 degrees counterclockwise, we get minus x. And then we can continue. Rotating minus x 90 degrees counterclockwise, we get minus y. And rotating minus y, we return back to x. We turned a total of 360 degrees, and so we're back where we started. Right now, you can notice that we can pull the minus signs from the last two terms to the front of the operation, because the negative sign is commutative. We already knew that, but it's good to see it still holds. So when we pull it out, we see that we really just have two copies of the same equations, but with a minus sign. The latter two don't really contain any new information, so we can get rid of them. Now let's inspect yx bar y further. If we multiply both sides of this equation by y bar from the right, we get yx bar equals minus x y bar. That's a new rule. Swapping the order of terms while keeping the bar at the same place negates the term. As you can see, that's almost what commutative means, but we just have a minus sign. This kind of relation is called anti-commutativity. The name doesn't matter too much, but knowing the names of these things make you sound cooler. Right now, we have only applied our operator from the left. Could we create a rotation operator that is applied from the right? Sure we can. Just multiply x bar y on the right. X bar gives 1, and we're left with y once again. So we see that the equivalent operator from the right is x bar y. But let's rotate once more just to make sure we don't get anything weird. We get yx bar y equals minus x. Swapping the orders with our new rule, we get minus xy bar y equals minus x. Y bar y is 1, so we can get rid of that. And we're left with minus x equals minus x. That's true, so we haven't broken anything. We're making great progress. One problem though. We've only been rotating by 90 degrees. Let's see if we can rotate by any angle now. We can apply the same procedure we used for the 90 degrees case, but now, instead of transforming x to y, let's transform it to a general vector v that makes a theta degree angle with the x-axis. Now, what do we multiply x by to get v? It's very simple, right? We multiply by vx bar. X is destroyed with x bar, and we are left with v. This is pretty standard stuff by now. We see that vx bar is the left rotate counterclockwise operator. Now let's expand the v term to get cos theta x plus sin theta y, all multiplied by x bar. We can distribute x bar inside the parentheses. Remember, because x bar is on the right side of the parentheses, we distribute it from the right. Okay, we get cos theta xx bar plus sin theta yx bar. Xx bar is 1, so let's get rid of that term. We are left with cos theta plus sin theta yx bar. This operator, when applied from the left, rotates any vector theta degrees counterclockwise. Just like we did with our 90 degrees rotation case, we can also find the right operator that does the same rotation. It's very simple. We just write xx bar v, and we see that x bar v is the right rotate operator. Expanding v, we get cos theta plus sin theta x bar y, and we can swap the positions of x bar and y and get a minus sign. This is the right rotate counterclockwise operator. So, as you can see, there are two ways to create counterclockwise rotations. You can either apply the left operator or the right operator. They behave exactly the same and produce the same rotations. And if you want to rotate clockwise, you can just put minus theta inside the parentheses of cosine and sine. Cosine minus theta is still cosine theta. That doesn't change. And sine minus theta becomes minus sine theta. And we see that Counterclockwise and clockwise rotations are very similar. We simply put a minus sign in front of sign. And that explains all of 2D rotations. You can rotate by any angle you want, either clockwise or counterclockwise. And you can do it either from the left or from the right. There is something we can do to make our equations more nicer though. First, notice that xy bar, which can be thought of as xy bar squared, is equal to minus 1. We can also do this for x bar y, yx bar, and y bar x. They all square to negative 1. Here's the trick. If you have something that squares to negative 1, which I'll call b, then you can write cosine theta plus sine theta b as e to the theta b. If you are familiar with complex numbers and Taylor expansions, this should be clear to you. If you are not familiar with those things, just think of this as a shorthand for cosine theta plus sine theta b. Now we can write our operators as e to the minus theta y bar x and e to the theta yx bar. And to get the counterclockwise versions, you can simply negate the exponents. Okay, I think we are truly done with 2D rotations now. There's just one more thing we should address before we go into 3D rotations though. Remember that xy bar and x bar y both square to negative 1. That means xy bar is equal to plus or minus x bar y. They are either equals or they are opposites. So which is it? Let's try both possibilities and see what we get. First, let's assume xy bar equals minus x bar y. We can write yx bar x equals y. That's just our normal rotate 90 degrees equation, if you remember. Now let's apply our candidate rule. Slide the bar and put a minus sign in front. Next, multiply by y from the left on both sides. We get minus xx equals yy. Okay, we're not really sure what xx or yy represents, but ignore the meaning of the equation for now, and focus on the implication. If we were to add a third basis vector, z, then because the same rule should also apply to z, we would get minus cz equals yy. But also, the same rule should apply between xx and zz. So, minus cz is also equal to xx. But minus xx and minus cz were both equal to yy. So, they must be equals. There is clearly a contradiction here. Let's try the other case now, choosing xy bar equals x bar y. Now we have y bar xx equals y. And doing the same thing, we get xx equals yy. And when we add the third basis vector, we get xx equals yy equals zz. No contradictions this time. Thus, we choose xy bar equals x bar y to be true. To sum up, we have xy bar equals x bar y equals minus yx bar equals minus y bar x. What this means is that changing the positions of unit vectors gives a minus sign, but changing the positions of bars don't do anything at all. But if the positions of the bars don't matter, it's like we are keeping track of a parity that has nothing to do with our equations. Consider this problem. You have 3 apples. You rotate a cube 60 degrees around the xy plane. How many apples do you have now? Replace apples with bars and you'll see what I mean. Let's get rid of the bars. From now on, we will consider x and x bar to be the same thing. Likewise, y and y bar are the same thing. All in all, we get xx equals yy equals 1 and xy equals minus yx. More generally, we can write e sub I equals 1 and e sub I e sub j equals minus e sub j e sub I. If two basis vectors are the same, they multiply to 1. And if they are different, you can't get rid of them, but you can swap them at the cost of a minus sign. Okay, it's time for 3D rotations. We add z to our list of basis vectors, which gives us xx equals yy equals zz equals 1, and xy equals minus yx, yz equals minus zy, zx equals minus xz. Let me put those rules in the corner as a reminder. Remember how rotation operators only had an xy term in 2D? Well, that's because we only had one plane of rotation in 2D, and that was the xy plane. Now we can also rotate around, for example, the yz plane with e to the theta yz, and also around zx with e to the theta zx. But there aren't just three planes in 3D, there are infinitely many planes. The three we have here can be thought of as the unit planes. Just like how any vector is a linear combination of the unit vectors, any plane is a linear combination of unit planes. Thus, rotation around the general plane can be written as e to the theta axy plus byz plus czx. Let's call that term b. We know from earlier that b squared must be minus 1, so that must put a constraint on a, b, and c. Let's try to figure out what the constraint may be. Okay, b squared is just b times b. Let's expand both b's and distribute. Whoa, that's a lot of terms. Something we notice right away is that terms with a squared, b squared, and c squared all have a term that squares to negative 1. xy, xy, yz, yz, and zx, zx, all square to negative 1. Let's replace these terms with minus a squared, minus b squared, and minus c squared. Okay, then we clean up the duplicate terms like yy and xx. And notice something in the remaining terms. We have two ab's, two acs, and two bc's. You can notice that one of the ab's have xz as its unit, and one of them has zx. We know that xz equals minus zx. So we see that those terms sum to 0. You can do this for the AC and BC terms as well, and they all sum to 0. So what we're left with is minus a squared minus b squared minus c squared equals b squared, which is equal to negative 1. That means a squared plus b squared plus c squared equals 1. That's the condition for b spelled out if we write b as a combination of our three unit planes with coefficients a, b, and c. And with that, we are done. Or are we? We should test our rotation operator now to see if it gives the correct results. Let's try rotating the vector x plus y plus z 90 degrees clockwise on the xy plane. I'll let the calculation play out. Okay, the results are in. Our answer is minus y plus x plus xyz. Wait, what's xyz? The result should have been minus x plus z. The x and y components rotated correctly, but z was messed up. And it makes sense, right? The z component shouldn't be affected by a rotation on the xy plane. Our operation fails to keep the z component unchanged. What can we do to revert z back to its original form? We have to multiply it by an x and a y, so that the two x's and two y's cancel out, and we get a z back. We'll just have to be careful on the order of x and y, so we don't get an unwanted minus sign. One way to do this is to right multiply by yx. Okay, that fixes the z component, but surely the rest of our calculation is messed up now. What we had previously was e to the 90 degrees xy times v. Now we need to multiply yx on the right. We can write yx in the exponential form as e to the 90 degrees yx. And at this point, something beautiful happens. The term on the right creates a 90-degree rotation clockwise on the xy plane, just like the term on the left. These are equivalent operators. They both do the same rotation, but now we are preserving the integrity of z, while letting x and y rotate freely. Let's do the calculation again. Okay, that's almost correct, but it seems we rotated 180 degrees instead of 90 degrees. It should be clear why that happened though. We applied a 90-degree rotation from the left and another 90-degree rotation from the right. What we should have done was to rotate 45 degrees twice to get a total of 90 degrees of rotation. Okay, let's do this rotation for real this time. The final formula for a rotation looks like this: e to the theta over 2b, v, e to the minus theta over 2b, where v is the vector to be rotated, b is the plane of rotation, and theta is the angle of rotation. People call this thing a rotor. And there we go. We invented rotations. And okay, here's a little extra. Some of you might be thinking, where are the quaternions? Quaternions are supposed to be this complex number field with 4 dimensions, 3 imaginary axes, and all that stuff. What we have here appears to be way simpler than that. But in reality, what we are doing here is almost word for word same in quaternion algebra. It's just written in a slightly different way. xy, yz, and zx are I, j, k respectively. And for weird technical reasons, vectors are written as purely imaginary quaternions, with xyz corresponding to I, j, k. And for example, in a game engine like Unity, the 4 components will correspond to the scalar xy, yz, and zx parts of our rotor respectively. All that said, I don't like quaternions at all. I believe the method we built makes way more sense than quaternions. Consider this. When doing 2D rotations with complex numbers, I rotates 90 degrees and 1 rotates 0 degrees. Our components aren't interchangeable or symmetric at all. And even worse, when using quaternions, we don't even use the real component when representing the vector. Isn't that weird? We used to use the real part in 2D rotations, so why did we drop it in 3D? And what if you wanted to rotate vectors in 4D or 5D? Quaternions won't generalize so easily to those dimensions. With our method, just add a new basis vector and you're good to go.